I have a voltage amplifier with passive feedback. But now I make a little bit more complex model for the operational amplifier. In the previous model, I didn't put any components that model dynamic behavior. It was just two controlled sources instantaneously, but no input capacitance, no poles and zeros, all this stuff. And now I want to make it a little bit more complex. So for example, in the current feedback operational amplifier, you find an impedance from the positive input to the reference, to ground. And you can already see that this impedance can be seen as a kind of attenuator in front of the amplifier. So this impedance definitely will influence the asymptotic gain. And here you find it in a model. Here I added a parallel impedance of the operational amplifier at the input of the amplifier, and I added a input impedance between the positive and the negative input of this amplifier, a pole in the output impedance, maybe a little bit larger, then you can read it better. So a pole in the output impedance, RO divided by 1 plus S tau, and also a pole in the transfer and at the same frequency. But this is not really what it is about. It's more about the effects of this parallel impedance at the input of the controller. So we can just put this circuit in Slicap for evaluation, and we want to see the effect of the parallel connection on the asymptotic gain. And that is what we expect. We expect that there will be an effect, because if the whole thing, let's say if the controller, if we select H1 as reference variable, then the controller behaves as a nuller, except for this part. This will always be a current flowing to ground if there is a non-zero input voltage. So the asymptotic gain will not be the ideal gain, which was solely set by RA and RB. So basically the controller never becomes a nuller because there's something outside this nuller. You can also explain it in this way. So I have this file for it. So what you see here, I have this this circuit. I didn't draw it in LT-SPICE, but that's why I showed you the circuit from the book. I can put the circuit data on the web page just for controlling. I set the loop gain reference to the current controlled voltage source, from which we know that the loop gain is meaningful, as good as can be. And I want to make plots of the gain, the asymptotic gain, the loop gain, the servo function, and the direct transfer as a function of frequency. So that's what I'm doing here to show you this. And you can put all this, you can calculate the gain, the asymptotic gain, the loop gain, the servo function, and the direct transfer, put them in a list and in a plot function, and it will plot it all together in one plot. So by running this, now the circuit data is clear. It's just the netlist and all the stuff expanded. So all the model of the operational amplifier expanded to all single components. Then here you have the Bode plots. Let's look at it. So the gain is blue, the asymptotic gain is red, the loop gain is black, the servo function is purple, and the direct transfer is green. And you see the asymptotic gain is not a straight line. And if you would calculate the value, this low frequency value would equal the ideal gain. But at high frequencies, there's attenuation because of this capacitor. Well, at low frequencies would also be a little bit less because of DC attenuation, because of the input resistance that was also there. Now, the loop gain is quite high at low frequencies. You see that this starts at 10 kilohertz. So it's about, well, let's say about 40 dB, which is about 100 times. I think if you calculate it, it's about 70. So the servo function is almost 0 dB. It's on this scale, you cannot see the difference. And there, where the loop gain is not longer larger than unity, then the servo function drops again. And of course, the gain follows then the servo function. But this is a topic that we will deal with next time, how all this dynamic behavior can be explained. The most important here is that you see, you can plot all these functions, and the asymptotic gain is not a straight line, what we expect from the ideal gain, but there's an attenuator, you can say basically outside of the controller, although the parts are part of the controller, you can take it outside of the controller and see that the asymptotic gain uh, uh, is attenuated at high frequencies. And here, of course, all the phase plots belong to that. Of course, you can see this also in the symbolic expression for the asymptotic gain, and that is here. The asymptotic gain can be decomposed now in the ideal gain and a factor caused by this input attenuator. Now, unfortunately, Slicap doesn't simplify this in the way you would like to see it, but basically, look, you have RA plus RB divided by RB. That is the ideal gain. And then there is another attenuation, Ri divided by Ri plus Rs, a DC attenuation between the source impedance and the input resistance to ground of the operational amplifier, and a time constant, the input capacitance, and the parallel connection of Ri and Rs. Let's look at the circuit to see if we can understand this. So this is Ri, this resistor here. And you see there's a DC attenuator in front of the amplifier, Rs and Ri. So it is modeled as G, but the one over the resistance. Yeah? So Rs and Ri is an input attenuator. And the pole of this input attenuator, if the controller for the rest behaves as a nuller, so if there is a huge loop gain, I would say, is like there is no current flowing in here, then in that case, it means that we just have a pole at the parallel connection of Rs and Ri and the input capacitance, exactly as we could see from the results given by the symbolic analysis.